Hello and welcome to the Academic Decathlon Science Section 3 explanation video, where we will be going through the human impact on natural resources. So let's get started with the ideas of the human population. So we started with factors that regulate population abundance and distribution, so biodiversity and how different populations of organisms are grouped together and how they also work in environments and such. So we also most specifically looked at non-human species, but now we want to start to look at human species and how we have impacted the environment around us or how we have used the resources of the environment. So we first need to look at the human population as a whole and how big it is and how that might have an impact on the Earth. And so, if we take a look at the United Nations World Population Prospects, we can see that the human population first reached 1 billion in 1804. So we can go ahead and look at this chart here, which is going to be really useful. We can see that in 1804 here, we have, let me actually get a little pen out here. In 1804, we have 1 billion people. Then we increased only slightly within the next few years. 1927 was 2 billion. Then 1960 is 3 billion, so we're getting faster. 4 billion at 1974, 5 billion at 87, 6 billion at 98, 7 billion at 2010, 8 billion at 2022, 9 billion is what we're estimated to be at 2037, and 10 billion is what we're estimated to be at 2058 at the median projection level. So the median projection level just means the middle projection of the worst case and the best case, or highest and lowest case in this specific instance. So we can go ahead and take a look at these annotations, or let me get rid of these annotations. Clear all. There it is. And so if we take a look at how the population has grown, we can take a look at some of the more specifics. So if you actually memorize this chart, it's going to be a lot easier for you on the tests. You'll know, oh, it doubled from 1974 to 2022 and so forth. But we can also see that it was in November of 2022 that we were reported to hit 8 billion. And you might need to know that. Some of these numbers of 32-year gaps or different things like that might be slightly different on the chart just because they happen in month spans, and so months can change how many years. But on the test, it's unlikely they actually do like 32, 31, 30. They'll probably do more reasonable numbers so that they're closer to what the chart is. And so we can look at the different addition of people. So we saw that 1 billion people were added every 12 years about from 1974 to 2022. Remember, that was the doubling. And we're estimating that it'll be a little over 10 billion by 2100. And so we take a look at all of these together, and we now need to look at how density dependent and density independent factors actually play a factor in human population growth. So we're going to be looking at how dense populations react to different stimuli, such as maybe food, or we'll see as it goes continuing on, income, so forth. So now we get into growth rate. So this is how much of the population has changed in a given amount of time. So for example, 1963, it was 3.6 billion, and we were growing at 2.1% per year. So notice 1963 is about here. The growth rate is the slope of this line right here. And so we can take a look at how fast it was growing, and that was 2.1% per year. But now in 2023, we are still growing, but it's at a lower percent. So we are adding 0.83 to 0.9% to our population every year. And so in most countries in the world, growth rates are actually decreasing. So because of that, we can see that even though there is a greater amount of people in the world, we're actually adding less people to the world per year than previous years. So the example they give here is that we're adding about 70 million additional people per year at a growth rate of 0.83 to 0.9%. out of our 8 billion. But when there was only 3.6 billion with a rate of 2.1%, we were adding 76 million. So as we can see, our growth rate is numerically lower, and so is our percentage, even though we have a greater population, because growth rate is based on the population of that year. So now we're going to look at some factors that look at what affects growth rate, and that is births, deaths, immigration, and emigration. So immigration is when people come into a country, and emigration is when they will leave a country. So imagine if someone is coming in from Canada to the United States, then that is immigration, and then emigration is when people move from the United States into Canada. And so we can actually represent our growth rate as a whole as births plus immigration in one section minus deaths and immigration in another section. So we're adding up births and immigration, we're adding up deaths and immigration, and we're subtracting them. And then we divide that by the total population. So for in this case, it would be 8 billion people, and or not for the United States, but for Earth as a whole. But we aren't actually looking at Earth as a whole, because imagine if like aliens were coming in as immigrants, that would be kind of weird. But the total population, for example, in the United States, it's about 334 million people. So we would do births, let's say there were like a million births, a million in immigration, and then there was like 500. Now these numbers are completely made up. They aren't actually accurate. And then we had 500,000 deaths and 100,000 immigration numbers. And so then we would have 2 million minus 600,000 divided by 334 million times 100 to get our percent growth rate. The reason why we multiply that by 100 is to get that percentage, because otherwise we would be in a decimal. Okay, so if this is the example they give, so if we have a village of 300 people, 10 deaths, 3 migrations, 4 deaths, 2 immigrations, we actually get 10 plus 3, so 13, minus 4 plus 2, 6, is 7 divided by 300, so growth rate of about 2%, because we multiply by 100. So migration and immigration are very important when analyzing individual countries. So we can actually look at population increases in the United States, and that actually accounts for 1/3 of all of the population increases in the United States. So immigration is very important to keeping higher or lower a growth rate in a population. So then if we're looking at all of the world, we can actually look, instead of looking at, obviously we don't have immigrants and immigration into the Earth unless we have like aliens coming from space that we don't know about, that like Area 51 found or something. But alas, we instead only look at birth and death rates in this case, and we can actually express for the entire Earth these things called crude birth rates and crude death rates. And so a crude birth rate is the number of births per 1,000 individuals on the Earth per year. So that means we could say have 2 births for every 100,000 individuals. So we would then be having that amount as our crude birth rate. And that's just a term to memorize. And the same thing goes with the crude death rate. It's also per 1,000 years, except it's the number of deaths per that many individuals. So then, if we exclude these things of migration, because no aliens are coming to Earth, remember, CBR minus CDR divided by 10 equals 10% growth rate. Now, notice this is per 1,000 individuals and not per 100. If it was per 100, we wouldn't have to divide by 10 because we were already by a factor of 100, if this was 100. And remember, 100 is the multiplier for percentages. So the reason why we're dividing by 10 here is because it's per 1,000 individuals, and we need to divide by 10 in order to get to 100. If we wanted to have the decimal approximation, we would need to divide by 1,000. Okay, so next up, we actually get to see growth rates over time as plotting them on a graph. And this is actually what is considered in the USAID guide the most effective way to see changes that take place in growth rates. So it's possible to see on a year-to-year basis how much are we growing. And so will the country experience positive growth or negative growth? That's up to if the birth rate is above the death rate, then there will be a positive. But if the death rate is above birth rate, then there will be negative growth. But if they're equal, then there will be no growth. Okay. Next up, we're going to talk about the population of lower and higher income countries. And so we can take a look at what's the difference between populations, especially in both their total population and their growth rates. So 1.3 billion people currently live in higher income countries, while as 6.7 billion live in lower income countries. So we can think about it as we have 8 billion, 1.3 of those is higher income, 6.7 billion lower income countries specifically. Now, we're actually including China and India in lower income countries for this case, and so that will actually affect how many people are in that because China has a very large population, for example, as opposed to the United States. Now, it hasn't always been so large that we've had a population difference, as you can actually see in this chart here. But as we've begun to have bigger growth rates in areas such as sub-Saharan Africa, we can see that growth rates have continued rapidly in those places, whereas in places like higher income countries such as the US, we've actually leveled off quite a bit. So this is actually a very useful chart here if we look at right before 1960, there was definitely more people in developing economies. However, the majority of new people has come, if we go ahead and look at the difference here, has come from developing economies currently. So notice how we're leveled off. I'm going to actually change this to red. We've leveled off in higher income countries, and we're projected to have leveled off still. And so if we look at our growth rates, we actually have in sub-Saharan Africa, or in areas of less developed countries, we have 1.5% per year of growth rate versus a 0.2% per year of growth rate. So much, much different. Okay, so now let's take a look at how population size impacts resource use. So for every one of 8 billion people on Earth eats, drinks, and generates waste products. So every single person is going to have these basic necessities of eating, drinking, and generating waste. So we all drink water, we all eat something, and we all poop. So we all have these waste. Now, we need resources in order to allow for these things. So even foods such as beans and rice, they all require energy and resources. So this is the main idea of this beginning section is that they all take resources to produce. It's not like we can all photosynthesize from the sun, which actually is another resource, but we don't get it. We need to take it from plants and animals in order to gain it for ourselves. So, especially not just these necessities are present, but also there's a lot of demand for wood, paper, plastic, steel, and energy to make homes, automobiles, and consumer products to give and receive services. So we all want a whole lot as humans. And this section is going to highlight that. So a lot of these things lead to environmental degradation, in which we are degrading the environment in order to gain resources for ourselves. Now, it's hard to quantify overall, this is saying that quantify meaning turn into a numerical value, all the impacts of 8 billion people. Excuse me, I need to sneeze. One moment, I'm going to pause. All right, so I just sneezed. That was nice. Okay, so environmental impact we were talking about, and how do we quantify this? Well, in a very basic way, at least to estimate, we say that the environmental impact equals the population times the resource use per person. So think about it. How many resources are we using in total? Well, it's the population times however many resources each person is using times the impact of the resource used. So say the impact is like 10. I don't know what unit it would be, but 10. And then there were 100 people in the population, and each person used 10 of this resource. So let's say for every person drinking water, that impacts the environment at a scale of 10, and each person is drinking 10 per day or something. And the population is 100 people. So that would be 100 times 10 times 10, which is 10,000. And so we would have 10,000 impact per day. So one good example is energy use. So in 1960, our population was 3 billion, as we went over, and the world fossil fuel consumption was almost 3 million tons of oil equivalents. And so 3 billion, 3 million, I mean 3,000 million tons. So 3 billion tons of oil equivalents. In 1999, world fossil fuel use was then up to 7,900 million tons of oil equipment equivalents. And then, while the population doubled, the use of fossil fuels more than doubled. So remember, 1998, that was our marker for, I believe, 6 billion people, I want to say. Yes, 6 billion people in 1998. So we had 7,900 million tons of oil equivalents. So fossil fuels more than doubled. I do want to note, though, this was on a question on one of our tests, and that was the question asked per capita, how much were our oil or energy equivalents being used? And the answer was it just increased. Because if you think about it per capita, which is per person, then with respect to population, our fossil fuels more than doubled, but they didn't quadruple. In order for the per person to have doubled, it would have had to doubled in fossil fuel or quadrupled in fossil fuels while the population doubled because 4 divided by 2 is 2, and that's a doubling. So we can then see in 2022 with 8 billion people, we're at 11,500 million tons of oil equivalents. And so we're even more, but not quite doubling per person, just more than doubling for the different rates. Then we have the consumption of fossil fuel, which actually has a lot of different environmental impacts. So remember, we're looking not just at the population and not just the resource use per person, but we're looking at as well how much does it degrade the environment. So the consumption of fossil fuel includes land and water degradation from extraction and air pollution and carbon dioxide emissions, and the carbon dioxide emissions result from combustion. So all of these environmental impacts have increased considerably during this time because we've been using more. So next up, we're going to look at what factors affect population growth. And so we're going to look at this nice little figure here. We're going to look, we talked about crude birth rate and crude death rate, just as a little review. It was per 1,000 in the population per year. The growth rate overall can be seen as the population in year 2 minus the year 1 divided by year 1 times 100, or we can do crude birth rate minus crude death rate over 10. So if it ever asks you what are two equivalent expressions, or what's the equivalent expression of CBR minus CDR over 10, you can say year 2 minus year 1 over year 1 times 100. And that will be the rate of natural increase. Then we have total fertility rate, which is the average number of children born to a woman during her childbearing years. So, how many children are being born for a woman on an average in uh, in the world, for example? Then we have doubling time. So, how much time will it take at the current growth rate for the population to double? So, once again, if we look back at this chart from 1974 to 2022, it took 48 years in order for the population to double. And so we're looking at, okay, how that doubling time was that. And so then we have infant mortality, which is the number of infants per 1,000 live births who die before their first birthday, which is probably one of the saddest ones to look at. And then we have life expectancy, which is the average lifespan of an infant born in a given year. So how long are people going to be living on average? And then we have percent under 15 slash greater than 65. So we're looking at what percentage of the population is below the age of 15 and above the age of 65. So that's why it's a less than and a greater than symbol. So first, we're going to take a look at fertility here. So we can actually look at all of humans as 8 billion people. They did a typo here. They actually pointed that out in one of their corrections. But we have a pool of 8 billion people. We have births and deaths as inputs and outputs, and it can be dependent on the birth rate and death rate. Now, the question is, how do we determine the birth rate? So we can take a look at the total fertility rate and see what's the average number of children that women are birthing, which in the United States it's 1.84, which actually is pretty low. Because if you think about it, when we're trying to replace two parents, we need at least two children in order to replace the parents in order to have a positive growth rate. So in the United States, if we were looking at birth rates alone, we should be decreasing in population right now because the deaths will be over the births. And so if we take a look at the growth rate and the total fertility rate, we can know that they correlate with one another. So higher growth rates usually mean higher total fertility rates. So then we're going to take a look at replacement fertility rate, which I was talking about earlier. Each woman must, on average, have about 2 or 2.1 in this case, children in order to replace two parents. Now, note, it needs to be 2.1 children because some children never reproduce. So we need some people to have 3 children, most people to have children. And so the United States, based on that, the population should be decreasing. But once again, remember, 1/3 of the growth rate of the United States comes from immigration. And so we actually add 1 million people per year to the population of the United States from immigration alone. So we are actually growing still as the United States, even though we have a low replacement fertility rate. Then we get into life expectancy and infant mortality. So life expectancy, we explained already, how many years is one going to live, given the average lifespan and the death rate. So usually, life expectancy is lower for men than for women, and this is usually due to greater hardships and dangers experienced in the workplace and different lifestyle choices. So, men make more dangerous decisions at work and more dangerous decisions in their lifestyle. So, men, be careful because you know what? We should probably be living longer too, and we aren't. So, that's a problem. Anyways, continuing forward, we look at what is infant mortality. Oh, well, that was fun. One moment. All right, I am back. So, infant mortality is the deaths of infants per 1,000 live births, remember. And so, usually these two factors together are a good representation of healthcare in a given country. So, if life expectancy is fairly high and infant mortality is fairly low, usually the country has high healthcare, versus if we look at crude death rate, for example, that's actually not a good indicator of healthcare because even if you have a high life expectancy and low infant mortality, a country could have a higher crude death rate simply because there's a lot more older individuals in the population. So a crude death rate might reflect that there are a lot of older people in the population. Whereas if we're looking at life expectancy and low infant mortality, then we can actually determine how healthcare is working. So United States actually has a higher crude death rate than Mexico, which actually shows that the US population has a higher, more old people in the country than Mexico does. And then we can look at over a dozen developed countries which actually have lower infant mortality rates than the United States. So, who in this list is actually doing better in healthcare in these ways than the United States? And that is Canada, Finland, Iceland, Ireland, Japan, Sweden, and France. So, actually, in the US, the infant mortality rate is 1 to 2 deaths per thousand greater than other comparable countries. So, the infant mortality rate, which is per 1,000 births, is actually 1 to 2 more than these other countries. And it's often uh, because not just because of how much we spend per capita on healthcare, but the United States actually spends more per capita on healthcare than these other countries. But universal healthcare and more generous allowances for time off during later stages of pregnancy, as it says here, are actually two reasons why the lower infant mortality rate exists in these other countries. We can also take a look at the large disparity in the level of healthcare given to Black Americans, Hispanics, Native Americans, and other minorities. So relative to whites. And this is also a factor into healthcare as a whole. And so we can take a look at what the actual infant mortality rates are, and that is 5.4 for the US per 1,000 births. And for Black Americans, though, it's actually 10.4. And for Native Americans, it's 8.2. So there's that disparity in healthcare, which is a big problem. So having less access to healthcare can actually impact and parental care, poor nutrition, minorities, lower socioeconomic groups, disproportionately exposed to pollutants. All of these contribute to higher infant mortality and poor health. So all of this shows healthcare as a whole. Okay, next up, we're going to talk about how many individuals or what's the age structure of different populations. So is a population on the whole usually like aging, or is it a very young population? Does it have a lot of young people? And we measure this using the 15 and 65 measurement, which we can go ahead and list here. So in Mexico, it's 24 over 8, which means 24% of the population is below the age of 15. And 8% is greater than 65. Whereas in the US, we have 18 and 18%. So it's relatively balanced. And so, note, we were talking about earlier how the crude death rate in the US is higher than that in Mexico. And that's because there's a lower amount of the population that's older in Mexico, which is 8%. That is greater than 65. And so, if we take a look at Mexico's age structure here, it's actually pretty close to that of the US. Even though it's 24 over 8, we're actually pretty close to Mexico. Because if we look at other countries, such as Nigeria, which is part of the sub-Saharan region, and it's actually experienced the highest population growth, we have 41% of the population is under 15 years old, and only 3.3% is over 65. So we can see that this is definitely a very young population, and this is actually reflected in higher growth rates. So we actually can understand potential environmental impact of the country by knowing how many young people there are and will be in a population. So if we think about like younger people are potential customers to soft drinks and fast fashion, and maybe automobiles and bicycles. So if there's maybe a greater percentage under 15, maybe that consumption will be greater. And so we can actually look to see, okay, what will the population also be looking like in 10 to 50 or 10 or 50 years? So with all of these, we're trying to look at, remember, potential environmental impact and where's the population going to be in the future. So, in order to visualize this, we can use division of different population groups in an age structure diagram. So I'm going to show you an age structure diagram real quick. This is the age structure diagram for the world right now. So as you can see, about 330 million males and 320 million females are in the world right now. And that stays pretty consistent uh, or for 0 to 4 year olds. And then that stays pretty consistent from 0 to 14 years old. Then it starts to dip more as you can go. So knowing that this chart is a lot like a pyramid, knowing that our population of our youth is a lot greater than the population of older people is really important to understanding. So each country actually has different age structure diagrams. And if the bottom is the widest and the top is the smallest, then that means there's lots more younger people than older people. And so the total fertility rate is usually in this case greater than 2.1 yeah, greater than 2.1. And so the growth rate is positive. And so we actually can call this a population pyramid in this case because it's a pyramid shape. And so this pattern actually occurs in less developed countries usually. So growth rates of 2 to 3.5%. So if we're looking at the United States, well, we don't have that sort of a diagram always because we don't have 2.2 to 3.5%, and we aren't part of those less developed countries. So we also want to look at the age structure diagram for Uganda, which is a good example of this less developed country. So if we look here, it's definitely this pyramid shape where it's definitely higher at the bottom and much lower at the top. And so this is very similar to Nigeria, Ghana, Haiti, and a lot of other countries. And so we see that where there are slightly more individuals in younger age groups than in older age groups, it begins to look like more like a column. So if it's only slightly more, so I'm going to go ahead and take a look at Japan here. Notice how this is a lot more flat or even inverse pyramid here. Um, we can look at how there's probably slower growth rates here, or it's reflecting an older age group. And so we're looking at a column, which this is actually called a stable population. So just remember, population pyramids means there's a high growth rate, and a column usually shows a stable population in usually more developed countries with older age groups. And so we can also remember that here the population of Japan, this is actually for Japan, is 123,294,513. So some groups are actually showing negative growth, as I talked about, inverse pyramid, such as Italy, Japan, and Germany, and they're actually showing a inverse pyramid because they have a total fertility rate below 2.1%. Or not 2.1%, just 2.1 people. Okay, so now we've finished up population, and I'd like you to take a moment to think about, okay, what does it mean for population to be growing in different areas of the world? How is our environment being impacted by that? And why is our environment being impacted? So I'm going to give you a moment. I'm going to tell you to pause the video right here, and you're going to go ahead and tell me. So go ahead and pause the video. Okay, so we are back and we are going to be discussing the elements of the earth, so the makeup of the earth, and we're going to also later be going over soil. So, the earth formed about 4.6 billion years ago, according to the geological record there. And so, within 500 million years, it heated up where there was a lot of molten rock on Earth. And so, think about all that lava that's flowing through about 500 million years after its formation. And how it formed was all of the heavy elements in that material, it all sank towards the center of the planet, while all the lighter elements went to the surface. And so they actually stayed after the Earth cooled up at the surface. So we have three distinct main levels of the Earth. That is the inner core, the mantle, and the lighter crust. And so the three main layers are those sections. And so if we take a look at this structure diagram here, we can see that the inner core makes up about 800 miles or 1,300 kilometers in radius. Then we have a 1,400 miles or 2,250 kilometers, and then we have 1,800 miles, which is 2,900 kilometers. And then the crust is the smallest by far, with 5 to 25 miles or 8 to 40 kilometers. And so we can see that elements are not uniformly distributed because there's a lot more heavy elements that are away from the surface and more in the center, whereas lighter elements were all towards the surface. And so even though the entire Earth is 35% iron, only 6% of the lithosphere, which is the crust and the top part of the mantle is the biggest section here, remember, only makes up 6% of that. So a lot of it is in the inside, a lot of that iron. And so we can see that a lot of more rocks, sand, and soil make up the Earth and are found in the approximately 100-kilometer thick lithosphere. So think about here, about 100 kilometers in, so just a bit more past the crust, maybe double the crust, maybe a little more than double the crust even. And we get into the mantle as well for that lithosphere. Now, in the lithosphere, we actually have rocks that undergo what's known as the rock cycle. So, as you can see, there's parts of the crust up here, but then there's magma that comes from the crust and mantle, the very lower parts. So, how it works here is let's start up here with weathering and erosion. So, if I can go ahead and label this, we have weathering and erosion first, which happens from snow or rain or so forth. Then it's transported down to the water, transport and deposition, and then there's sedimentation underneath the water here, which can happen due to water compacting that different rocks underneath. So it's compacting and cementing it. Cement is what we use in our sidewalks, and it's harder. Think about that. Then after cementation, it's sedimentary rock. Then after sedimentary rock, now remember, sedimentary rock has lots of layers, and this actually reminds me of a question where you could be asked in an interview, what rock do you think best represents you? And you could answer with sedimentary rock because I have lots of layers. So use that one in an interview, it'll be very nice. And then if we take a look at sedimentary rock, it actually undergoes burial, high temperatures and pressures. Then we get to metamorphic rock. So just remember, metamorphic is at the very bottom. It's in the mantle, metamorphic. And we then have melting into magma. And then the magma crystallizes. So imagine like obsidian coming from lava. Well, that's almost like crystallizing, right? So you can imagine obsidian as a crystal. Then it becomes igneous rock, which is right after the lava. So if you know what ignite is, like fire, it comes out of the magma. And then it's slowly uplifted to the surface, and we finally get to back to weathering and erosion. So that there's the rock cycle. And so we get to see that the lithosphere is one of two primary sources of elements in the biosphere. So there's also a major source in the atmosphere, which elements exist in gaseous form. So we have the biosphere takes from the lithosphere and the atmosphere most. So if you're ever asked on a question, what are the two primary sources of elements in the biosphere, you would answer lithosphere and atmosphere. So in in the atmosphere, we actually have three of the most abundant gases in the atmosphere are nitrogen, which makes up 78%, oxygen, which makes up 21%, and then argon, which makes up 0.9%. Carbon dioxide makes up 0.03%. So it's actually a trace gas. So we think there's so much carbon dioxide, really, even just a small amount of carbon dioxide can really impact the way our atmosphere works, even though it's just a trace gas. And so we call carbon, hydrogen, and oxygen often the building blocks of life because they're actually the most abundant in plants and animals in the biosphere. They make up cell walls, membranes, etc. And so they're often directly obtained from air and water or recycled from other plants and animals. So think about if you're eating a plant, you're eating some carbon and hydrogen and oxygen there, and you're getting some of those elements. Then we have some other essential elements which we can find and that are very important. And those include nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. So NPPCMS, NPPCMS, NPPCMS. So try and use that acronym to try and remember the different elements that we need. Now, you don't want to mix up the different elements either because we have some other elements here which are different. And so we look at the six essential elements are usually greater than 0.1% of an organism's dry weight. And then there are also seven more plant essential elements which are required in small quantities. So the bigger ones, the ones that are needed in more quantity, is macronutrients. So macro meaning big, and then micro meaning small. So we don't need as many small quantities. So these include manganese, iron, copper, zinc, molybdenum, not cobalt. They actually made a correction to this in the packet. It's actually chlorine and boron. So just remember McZ McB. So you can remember it that way. So like Old MacDonald had a Z, and then Old MacDonald also had a B. Uh, Hopefully that helps you remember. So these are needed in small quantities, as I said. So these 16 essential elements actually are needed in varying proportions, and a lot of these we get from the atmosphere and from rocks, so lithosphere and atmosphere again. And we also need to recognize, though, that soil is very important, an important source for these plants. So a lot of these elements actually are taken up by plants in ionic form. So if you're ever asked a question on in what form are nutrients taken up in plants, they must take it up in ionic form. So that just means that they're an ion, which means they've lost an electron. You don't need to know that for the test, or they've gained an electron, but they aren't in their natural state, is the point. They're in an ionic form, not an atomic form. And so all of these plant essential elements have an aqueous phase, which means they are in ionic form and they're in water. So they are soluble in water. They have this polarization in water that allows them to be taken up. Now, soil water, which is actually water in the pore spaces between the soil particles, this allows for the exchange of these dissolved elements. So dissolved elements are just elements in their aqueous phase. And this allows for the exchange from the soil to the plant roots. Water allows all of it. You take in water with these ions or these ionic form of different elements, and we're able to use them as resources, or plants are. And then we eat plants. Then there's also the hydrologic cycle, which actually helps cycling these elements. So there's weathering and erosion, which actually helps transport these elements via water and wind. So remember that weathering and erosion transports the basic building blocks to the essential elements for plants. And then once they're in their aqueous phase inside of water, they are carried through the hydrologic cycle, taken in oceans or plants on land. And then the weathering of rock can be accomplished by water, wind, acid rain, or other chemicals, or even roots of growing plants. So a lot of weathering happens from these causes. Then we're going to go ahead and get into the cycles of calcium, magnesium, potassium, and sulfur. So, quick quiz. What type of nutrient are these? Is it macro or micronutrients? That's right, it's macronutrients because we can see here calcium, potassium, magnesium, sulfur. And so we are going through these different calcium and magnesium and potassium and sulfur cycles. And to begin, we want to start talking about rocks and decomposed vegetation. So calcium, magnesium, potassium usually come from that vegetation. And so calcium and magnesium often happens in limestone, dolomitic limestone, and marble. So you can usually remember this by the fact that in limestone, there's the first three, calcium, magnesium, and potassium. And then we'll get into, or just calcium and magnesium, sorry, are in limestone and marble. And then calcium and magnesium are usually abundant in ecosystems with lots of different limestones and other rock types. And they're also a large component of what's known as terrestrial dust. So a lot of that dust that you might find in the air at random times, especially that was found in the dust bowls in the 1920s and 30s, you can find lots of calcium and magnesium. So you might be asked which elements were most found in the dust bowls in the 1920s and 30s, and you would have to answer calcium and magnesium. And so you can remember that because they are part of terrestrial dust, and dust happened in the dust bowls, and they often occur in rocks and decomposed vegetation, of course. And so there was a lot of westerly winds that actually deposited in the central and eastern states. And so heat, drought, and wind, coupled with poor agricultural practices, actually led to the destruction of that natural topsoil. So in these dust bowls, there was destroying the soils down below, and this caused the calcium and magnesium to be picked up as dust and then carried away in the dust bowls. And so they are often combined with organic compounds and they don't leach easily, so they don't come out from water very easily. But they potassium is susceptible to leaching from plant tissue and soils, so coming out of the plant tissue and soils themselves. And especially these are lost. This is lost if it has lots of systems with phosphorus. So if there's lots of phosphorus in the area, then it's often susceptible to leaching, which is where it's being lost. And so then we get into the sulfur cycle, which is actually very similar to the nitrogen cycle. So it has a gaseous component, which is sulfur dioxide, and then plants take up the sulfur through the sulfate anion. Notice how it's an ion again, and we talked about earlier how it's ionic compounds which can be taken up by plants. And so then there's anthropogenic deposition of sulfur, so that just means human deposition of sulfur is greater than the deposition of nitrogen. Uh, so that means it's being deposited right uh, into the atmosphere, I believe. And so clean air regulations have actually lowered sulfur deposition since 1995, but it's still greater than the deposition of nitrogen. And so we also know, along with nitrate, sulfate actually composes or comprises acid rain. And so sulfate, just like phosphorus, is actually very easily leached from soils and ecosystems. And one main difference, however, is that there is a pool of sulfur in lots of rocks and minerals. And especially from volcanic emissions, we see lots of emissions of sulfur. So that's one of the main differences between sulfur and nitrogen cycles is that sulfur is going to be coming up from rocks and minerals and from volcanic emissions into the atmosphere. So that was the first part of science section 3, and we're going to take a real pause here in, and then we're going to get into some soil. Alrighty, so we're going to start going over a bit of soil. So first we're going to start by talking about what exactly is soil. And so we know that it's the stuff that covers the earth, but it actually connects a lot of the different parts of the earth. So for example, biology and underlying ecology as a whole. So it actually benefits plants, animals, ecosystems, and human beings in several ways, including the fact that soils are a medium for plant growth. So remember, this one is easy to remember. Plants grow out of soil. Soils serve as a primary filter of water as it moves from the atmosphere into rivers, streams, and the groundwater system beneath most land surfaces. So, if you think about it, it actually is where a lot of the water accumulates before going into the atmosphere or after being in the atmosphere into rivers and streams and into soils. And so it's this connecting point between the atmosphere and lots of different groundwater. Then we have a lot of different living organisms that can be in soil, including bacteria and fungi and insects and other animals and such. And these actually contribute a lot to the biodiversity of the ecosystem. Remember, in section 2, we talked a lot about biodiversity and how this is very important for an ecosystem. So, soils actually act as organic matter recyclers. So this means that they are recycling organic matter to be reused in other ways. And so it takes dead plants and animals and it's using it as energy. So maybe a fungus can uptake some of the dead matter and make it into food for itself. And so it breaks down this organic material and makes nutrients that benefit plants. Remember, up here we talked a lot about a lot of the different macronutrients that are needed, such as nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. And then the micro, the manganese, iron, copper, zinc, molybdenum. This isn't actually cobalt, this is uh, chlorine or chloride, and then boron. Um, so we have a lot of these different needed essential elements, and so a lot of these will come from the soils. And so, like for example, if you're looking at sulfur, that comes from the soil as sulfate anion. Think about nitrogen. Well, nitrogen is the same thing. Deposition of nitrogen goes into the soil. Okay. And then, oh, excuse me, one moment. So, as we were saying, there's this one more other way which soils can connect the different functions of animals, plants, ecosystems, and humans, and that is that they filter chemical elements deposited from air pollution and sewage from household waste systems, and this actually retains some in the soil and it releases some to the atmosphere or above in the groundwater below. So remember in section 2, we talked a bit about nitrogen and how it can go from the soil to out into the gaseous form, N2 and N2O. This was called denitrification. And so it turns from nitrates into the gaseous form of nitrogen. And this is where soils come in, is a lot of different pollutions have a similar function, is in which they come from household waste systems or maybe air pollution or different things like that, go into the soils, and then the soils release them and take in some of those pollutants. So we need to be aware of that when we have pollutants. Next up, we're going to describe what exactly is soil and what are the soil horizons. So, we often just think of soil as soil, but there are lots of different types of soil that we can have. And they actually, we, when we move and see that soils vary across a landscape, they actually vary only a few meters in depth, and so they usually have these things called horizons or different layers almost. It's almost like how we have layers of epidermis or skin. And so we here have from 0 inches to 2 inches, we have the organic layer usually forms. And so this is the O horizon, and this is usually comprised of needles, leaves, woody material, and animal bodies or droppings. So think about this one as everything that's on the forest floor. So if it's a forest, then it's usually going to have an organic layer because it has a bunch of organic matter that surrounds it. And so then, usually in most environments, though, we have the top layer of soil, which is the A horizon. So if organic doesn't exist, it's usually just the A horizon, which is 2 to 10 inches below the surface, unless it's on the top, in which case it would be 0 to 8. And so usually, this horizon is actually, it has organic material, which is known as humus, and mineral, which is rock derived. So a little bit of rocks, a little bit of organic material here, humus. And so this is usually mixed together. And this can actually be done naturally or by human activity. So earthworms and plant roots usually do this mixing of humus and rock-derived soil. And then we also have human activity, which can plow fields. That's what they're doing, is they're mixing together the mineral and organic material in order to make it suitable to grow things. So usually O horizon is even more comprised of organic material. which makes it more suitable. Sometimes there's an E horizon under the O or the A horizon. So sometimes E can be either below O or below A here. And it's usually characterized by what's not there. All the chemical elements pretty much or most have been leached out, so they've left that type of soil and so it leaves it a very light color. And so from from the E horizon, usually that organic material uh, from the E horizon usually goes down into the B horizon. That's what it means by leached, is it goes down into another area. And so these accumulate and they have undergone weathering. And so all soils have a B horizon, whereas E horizons usually only occur in more acidic soils. So if you're thinking about, okay, when does an E horizon happen? You can think, okay, well, there's leaching happening, which also connects to, okay, well, then the soil must be acidic because it is leaching, and that leaching is the effect of the acidity of the soil itself. Now, all soils have a B horizon, which is where clay, iron, and aluminum and other compounds accumulate after being leached out of the A horizon by rain. So rain will come down, it'll soak all of that matter up, bring it down into the B horizon usually. So from the A horizon, or even it could be the O horizon. So sometimes O and A can fall all the way down into the B. And if there's an E horizon, O, A, and E can be leached all the way into the B horizon usually, where there's lots of clay, iron, aluminum, and so forth. Then we have C horizon, which is the least weathered soil horizon, which occurs beneath the B horizon. So this is basically just saying that it hasn't been weathered, which means weather hasn't affected it. That's how you can remember it at least. So it's not being shifted around, it's not being changed. All of the matter that's being in it is not being soaked into the layers below it, that weathering. And the reason why is because it's so low down here in the layers, which it B occurs from 10 to 30 inches, and then C occurs from 30 to 48 inches. And so we here can see that the C horizon is similar in composition, at least, which means what it has inside of it is very similar to the parent material, which is where all of the rocky material from that soil is actually coming from. So if you're thinking about, well, where does all of the rocks and such that make up these soils come from? Well, they come from the layers below, which is the parent material. And now, the sea horizon in some humid regions could contain plant roots and microorganisms, but usually these only extend to the B horizon. So, if a question might ask you in a humid environment, where might plant roots stretch to? And it'll say O horizon, A horizon, B horizon, C horizon, or bedrock. And then you would answer, oh, it's the C horizon because in it says here that in the humid regions, C horizon can contain plant roots and microorganisms. Then we have different vegetation that we actually see in different biomes of the earth, which are largely dependent on the composition of the soils. So if you think about humidity and the overall temperature are what define what a biome is, right? That's what we learned in the previous section up here in section 2. If we go up to the biomes section. So if we look at these, mean annual temperature and mean annual precipitation. So humidity and precipitation are very connected here. It's how wet the areas are. And so if we go back down here and we take a look, these different soils often have different compositions, which allow for different vegetation to occur in different parts of the world. And so, if certain soil horizons are existent in an ecosystem, then this can actually influence how not only plants grow, but also how pollution is accumulated in those areas. And then we get into state variables and soil formation. So what actually forms soil and what are the important aspects that make up soil? So the soils form in two different directions. So you can think top and bottom. We have breakdown of rocks and minerals. They actually allow for those rocks and minerals to make up the soil from underneath the ground. And then as things deposit, such as organic matter and vegetation and animals, those all contribute to the formation above. So usually, organic matter in soil is quite low, except for organic soils in bogs. However, it actually greatly affects many soil properties. So, organic soils, although they are uncommon and organic matter is scarce in a lot of different soils, they're actually very important and affect soil properties quite a bit. So, here are the things that affect soils overall. We have state variables, they're called. So you can just think of these like state variables. A state is a big area, so you can think of, okay, these are very important parts of soil, state variables. So the literal definition is important factors that cause a soil to progress from an initial state. And so the nature of soils are affected by these things: parent material, climate, topography, organisms over time. So, if we want to visualize this here, we can see that climate is going to influence the soil, the parent material from below, so what is below it, is going to impact the soil. The plants and animals that surround it is going to impact the soil. The time, how much time has this soil just sat alone or hasn't been messed with? And the topography, what's the geography like? Is it on a mountain? Is it going to be influenced by a ton of avalanches? We don't know. And so we're going to go ahead and talk about each of these different state variables here. So, parent material is usually made up of the rocks and minerals immediately below the soil. So, bedrock is the solid rock underlying the soil. We saw it up here. It's below the 48 inches mark, and you can think about it, well, if you've played Minecraft, this is probably very easy to remember because, well, bedrock is unbreakable. It's all that very hard rock at the bottom. Now, in real life, bedrock isn't actually unbreakable. I know, crazy. But we can see that the bedrock and parent material can be synonymous or different. So that bedrock can make up what the soils are made up of, but there is also other sources that the soil can get to be parent material, such as in this case that the packet outlines, which is that if glaciers have spread a layer of rock and sediment over the bedrock, so there's another layer of this sediment and rock that's above the bedrock but below the sea horizon. And no, they may test us on this. Surface organic is O, that's easy to remember. Surface is A, subsoil is B, substratum is C. So you can probably think about it as like, okay, well, I know surface is going to be easy because that's the next after organic. Organic is obviously going to be the top, but then we have A as the surface, that's the top. And then we have the subsoil. So we can think soil, okay, that's near the top, but it's sub, so it's below. It's below the surface. And then we have the substratum. How I would remember this honestly is that it's a longer name, substratum. And then that means it's lower down, it's in the sea horizon. And then bedrock, I'm not sure why it's called an R horizon, but they they like to do random names for things, so you can probably remember that. And so if we're taking a look at this back to this idea of what makes up parent soil, well, bedrock can make it up, or this other layer that may be caused by glaciers could be there. So, okay, good, I am recording. Okay, for a second I was very worried I was not recording. But continuing forward, we can see that the parent material actually makes up, well, what's going to make up those upper horizons before all the chemical and physical weathering and biological activity is going to happen. So think about all the plants and animals that are going to die and going to make up those soils. Well, the parent material is basically what it would be without all of that stuff. And so different parent materials make different kinds of soils. So here's a few examples. Quartz sand as a parent material will make poor, nutrient-rich poor soil. And this is actually common in the Atlantic coast of the United States. So you might be asked a question like, on the Atlantic coast of the United States, what kind of parent material might arise in the A soil horizon? Don't let the wordy messaging mess you up. Parent material, it's gonna be quartz sand because it's on the uh, Atlantic coast. Or it might ask you a harder question, like if quartz sand parent material makes up the C sublayer of the soil, then what kinds of plants would most likely be able to thrive there? And then they might give you like a bunch of like different plants that they could take from another section, which let's say they go back, trying to find it here. Here. They ask about forest succession. So they might ask, oh, well, a moss, or which is most likely to form? Moss, tree seedlings, jack pine, balsam fir, paper birch. Now, you'd want to answer moss because this is the earliest form of succession here where less organic soil is being formed and mosses don't require as much soil as others, and so you can infer this. Now, that would be a very, very hard question to ask, especially because it's combining two questions, but you never know. Combining those concepts really helps you remember them overall and remember, hey, well, now I remember that mosses are very early in succession in a new community, and then I can also remember that the presence of quartz sand in soils means that it's going to be nutrient rich or nutrient poor, not nutrient rich. Don't listen to my mumbling. But then if we have calcium carbonate in the soil, so limestone, we actually will have a lot of calcium, such as the Lake Champlain in northern New York and Vermont. And this will allow for a lot of agricultural activity. So think about New York and Vermont. I don't usually think of those as like really high agriculture, but in this case, they are. So Lake Champlain means calcium carbonate, and that means an abundant supply of calcium. So hopefully you remember, oh yes, calcium is very good for me. I need to drink my milk. And so that milk will be very nutrient rich and very good for agricultural activity. So then we want to start to talk about climate. Climate is the second state variable that will impact the type of soil that's forming here. And so we can see that an average temperature is usually very important for soil formation. So higher temperatures mean more weathering and other soil forming processes. And then if soil freezes and thaws, there's going to be a more mechanical breakage of rocks and minerals, which creates new rock surfaces for chemical weathering. So what does that mean? Well, it means higher temperatures, soils will break down more, and they're probably going to have some more weathering, which means like leaching and water will come down on them and affect the soils a lot more. Whereas if uh, a soil is freezing and thawing, that means more rocks and minerals are going to be breaking up, so that parent material will be forming new soil, and our soil will be like, yay, we're forming new ones. Now, that doesn't absolutely imply more organic matter or even supporting better agricultural activities or even being nutrient rich, but it does mean we're having more soil formed. And so this all influences how leaching occurs. Now, with more water, that means there's going to be more leaching. So if there's more water will be pulling those resources down from the soil layers and bringing them into, say, bringing it from the A layer down to the B layer. And so usually warm tropical soils experience more leaching than cooler soils. So if you think about it, warmer, it's going to be broken up a little more. Water is going to be able to seep through it a little more, and that'll make it a little easier. So then we also have the fact that climate affects soil formation by influencing vegetation and allows vegetation to decompose after it dies. So this climate will impact, well, what is the vegetation here? Well, that means some more organic matter might be present in this environment. And then, well, how fast is that vegetation decomposing? Is that going to affect the soil over time faster or slower? And that's another one of our state variables, remember, is time. Next up is topography, or surface configuration of a landscape, which influences soil formation even more. And so, as I mentioned earlier, if there's steep slopes, then there's going to be a lot of erosion. And so we have might have more material moved overall, such as in landslides. And I don't know if avalanches really was the right word when I described it earlier, but I was thinking about snow for some reason, so we can excuse it. Anyways, we have landslides, which are actually hazards to humans. Obviously, we don't want a bunch of soil falling on our heads now, do we? I feel like now someone's gonna put soil on my head for no reason at all, and I'm gonna feel so offended when that happens. Anyways, continuing forward, if we take a look at soils being subject to landslides, we can see that uh, there's soil being distributed to the areas around them at frequent intervals. And so, even though these dangers are present, people can be, let's just say, not so smart. And they'll build all these amazing structures and be like, oh, look at my amazing house. Oh my goodness, there's a landslide. What is going on? Please don't hurt me. Ah! And then it will hurt you very, very badly. So, people are then very like, when the soils destroy them. But if the soils are relatively horizontal, I mean, you can build there. Think about that one parable of, or not a parable, but really just a metaphor in a way of building your house on the rock versus building your house on the sand. This is the same thing. Don't build your house on a cliff that's about to have a bunch of landslides. You gotta build your house on the horizontal soil. So, we have steep slopes accumulate more material at higher elevations, and then the soils on the windward side will experience lots of water deposition, so lots of water flowing through on that way, uh, of precipitation going on the leeward side. So we've got the windward side and the leeward side. The windward side is where the wind is blowing all this stuff, and so the water is going to go that way. And the water isn't going to go the other way, which means more erosion on the other side, on the wind blowing side. Okay, next up, we're going to actually talk about, well, what are the, oh, we don't need to get to figure 62 yet, I don't think, because that's for organisms. But we can talk about soil texture and what makes them up. So we have, this is a very useful chart, so please try and remember it. We have gravel, sand, silt, and clay. Now, gravel and larger fragments are greater than 2 millimeters in diameter, whereas sand is going to be just about 0.05 to 2 millimeters, silt 0.002 to 0.05 millimeters. Then we've got clay, which is less than 0.002 millimeters. And so we can actually see with this scale here, clay is like super small. And then we've got silt, sand, and gravel. So you can probably imagine, oh yes, gravel will definitely be the biggest. And then we have sand, and then silt. So just think of like the sand kind of shrinking down to silt, and then there's clay. So think about how movable and like changeable clay can be and how you can rearrange it. Well, that can be a connection in your mind. Well, it's shapeable, so that means its particles must be really, really small. So then we're going to continue on to talking about organisms making up soil ecosystem. Now, this next little sentence here, organisms account for 80 to 90% of the biological activity in soils, fungi, bacteria/archaea, and protozoa, single-celled organisms, including algae. So this was actually a question I got wrong in at my competition, I believe, actually, for Academic. And you see, I didn't realize that it was fungi, bacteria/archaea, and protozoa there. And so this made up 80 to 90% of the biological activity in soils. So you just got to remember, well, Fungi. Okay, this is pretty close to bacteria and archaea and protozoa. Now, what formed first in the earth was bacteria and archaea and protozoa. Now, I can't say the same for fungi, but fungi I feel like is like very similar in my mind to bacteria because like I don't like fungi and I don't like bacteria. And so, even though fungi is great, like in bacteria is great, but like in my mind it has a negative connotation. That's just how I'll remember it. And these organisms make up 80 to 90% of the biological activity in soils. So, if you're ever asked which ones make up the greatest amount of activity, it's gonna be fungi, it's gonna be bacteria slash archaea, and it's gonna be protozoa. Then we actually describe what protozoa actually are, which are single-celled organisms, including algae. So, yes, we know what protozoa are now. And what a lot of these organisms do is they take a lot of the waste from plants and animals. So whether this means dead plants and animals, or maybe the excretions of animals, which animal waste is called detritus, and they use it and they make organic energy from it because they're breaking down the organic matter and then they're making some energy, just like lots of plants get their energy from the sun. Well, these these excuse me, these organisms make up some energy from the poop of other organisms. How tasty. Anyways, we might find that some soil organisms are herbivores. So we've got eating plant roots and above ground parts of plants. So this could include, like, I don't know, a worm, but I don't think even worms do that. But majority of soil organisms are actually detrivores, and so they consume dead plant and animal tissue. So that just means, oh, lots of dead stuff. We eat it. That's what a detrivore is. And notice detritus and detrivore is actually very close. So you can remember it in that way. So a grassland, it then goes to describe different areas, so such as a grassland meadow. So grassland meadow could have 10 times the mass of soil detrivores as herbivores in the first 15 centimeters of soil. So you've got to think about, okay, how much more soil detrivores are in the soil than are herbivoid herbivores. So we can find in the first 15 centimeters of the soil, which we can kind of convert these numbers here to those same numbers. So we have 10 inches. If we're thinking converting it to centimeters multiplied by 2.54. So that's about 25 centimeters versus where was I? Where was I? 15 centimeters. So we're going into about the A surface, right? We're going like right here, and we're finding these different organisms, these specifically the detrivores, in much greater numbers than the herbivores. And then we see what role does bacteria play? And this they play in liberation of nitrogen or sulfur from organic matter, and this actually allows a lot of material to be used by higher plants. So bacteria is taking down a lot of these organisms, these dead organisms, turning their nitrogen in using denitrification into the atmospheric nitrogen, for example, as we learned about in section 2. Then we have what are the other organisms in certain areas, such as the temperate zone. So in the temperate zone, we have macrofauna, which are large animals, and more specifically, the macrofauna in the temperate zone are earthworms. So macrofauna are relative to other organisms inside of the soil. Earthworms are pretty big. So if you think about like a bacteria versus a earthworm, yeah, an earthworm is going to be much, much bigger. And that's why it's called macrofauna. Fauna meaning animal, and then macro meaning big. And so earthworms can actually take in a bunch of soil 2 to 30 times their own weight each day. Holy moly, that's like a lot of soil they're taking in. So they're taking it in, And then guess what they're doing with it? They're pooping it out, baby. Yeah. So just take that in. All worms do is just consume soil and let it flow through their bodies. Okay, I should stop talking. So, earthworms, they actually enrich soils by doing this. So they only partially digest all of this stuff that they ingest, and then they excrete nutrient-rich organic matter, which the plants are like, yo, we love worm poop. And they're like, okay, I'll take it. And so they grow much better. So earthworms then also aerate the soil so they make it more airy. They give it some air, give some breathing room. Yeah, we need that breathing room in the soil. They improve water drainage, so they're allowing the water to drain easier. Now, think about if it's being more airy, well, more water is going to be able to flow through it. And then it also mixes upper layers with lower layers. So imagine if a worm, let's call our imaginary worm here. Let me draw a little worm here. He's going to be a red worm or a little worm here. He's chilling in the sea area, which I don't know why. I don't think they would actually appear. Let's actually kill this worm because he should be dead because he can't live there. Let's say he's up here chilling in the lower layers of the A soil horizon here. And he's like, "Yo, I actually really want to eat some soil up here, but then I want to go up to the organic layer." So, he'll go ahead and he'll eat some and he'll start to travel up and he's gotten a little longer here because he ate some soil. And so then by the time he gets up there, he's now in the O horizon and we can see that he's gonna excrete some of that good old soil from the lower layer. And so he's starting to mix and then he's gonna eat some more and he's gonna bring that down to layer A. So Tom here is doing some great mixing for us. He's given us the poop we need. I should really stop. Okay, let's continue forward. So, earthworms not only move that mixing of layers, but they also are sensitive to acidic soils, and they actually do great in moist habitats that are approximately pH neutral. So in acidic soils, I'm going to quiz you real quick. What happens between the different soil horizons when the soil is acidic? What horizon usually appears? Is it O, A, E, C, or R? I'll give you a few moments. It is da 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 da. It is the E horizon. And so this is where the E horizon is actually accumulating all of the elements because it's more acidic. So I hope you got that correct. It was the E horizon. Now, sadly, the earthworms do not thrive in E horizons, even though their name starts with an E. Okay, next up, we can talk about time. So, how does time actually influence soil? Well, if we actually have a long amount of time, then soils have usually been able to undergo a lot of separation into different horizons. But if there's more time, they develop more horizons and more characteristics. So, grassland soils that support much of the food and livestock feed produced in the United States are still relatively old soils. So, old soils actually are really good because they've gotten all these layers and they're able to produce agriculture very well because they've undergone that separation. So they actually can support food and livestock. And it's because of those hundreds of thousands of years that they've experienced formation. They've developed those thick A and B horizons. So if you're ever asked on a question, well, we have a very large A and B horizons in this soil. How much time do you think has passed in this soil? Is it A, a very little amount of time, B, a little amount of time, C, a fair amount of time, or D, a quite long time? And the most accurate answer would be D. So, as we see, time really helps with creating that large supply of nutrients. Now, if we're thinking about, well, what brings back all the soil? Well, we can even go back to section 2 for this in the succession little talk here. So, in succession, we talked about how uh, a like glacial scarring or volcanic eruption can just wipe out the surface. It can destroy it. And so there's got to be bare rock, no soil, and it's a lot of plant species that are best suited to grow without soil, right? So such as lichens, mosses, and other small plants, right? So this, where we have primary succession, this is where were we? Our little soil here exists. If there were catastrophic events, then we aren't going to be having very thick soil horizons, now are we? So finally, we've got a little summary here where it just tells us that all of these state variables come together to affect a lot of different soils and different ecosystems, and overall, they're classified into different types, like the presence, absence, or thickness of different horizons that which were described. So, we can now finally go back to this figure in figure 2, which is actually very fascinating, where let's start up here where erosion is happening. Remember, on the hills, erosion happens more often, and this can happen even in the tundra area. Some methane is being excreted here, and so is some CO2, but it's also being taken in by the peatland. This peatland is this edge between the erosion area and the forest, right? And so then we've got forests in which CO2 is being taken in because there's trees, and so trees are really loving to eat up that carbon dioxide, baby. So we've got root exudates and then aggregates and then microbes. So what are the root exudates? Well, they are the aggregates, which are made up of microbes. And these microbes are what can process a lot of the organic matter. So whether it's dead or some are herbivores and can eat up the plant roots and then excrete a lot of different parts of the soil, which remember we talked about. Remember soil animals, we have things like earthworms here, which love swimming through that soil. And then we have below ground litter, which is a lot of that forest droppings. So in the forest, remember, we have that O horizon, which has a lot of leaves and organic matter at the very top, which can be falling down into lower layers of the soil. And now, when we harvest a lot of the land and forests, we release a lot of methane and CO2, and agriculture can do the same thing. And so we see that these unprotected light fraction organic materials are being formed from the soil animals and from the aggregates and so forth. And sorbed mineral protected organic compounds can come from the aggregates as well. So a lot of this is just summarizing what we've already gone over. So finally, in our discussion of soil here, we get to talk about soil degradation. So, a lot of people like to use soil for a lot of different things, including agriculture, forestry, and other human activities. And so, this actually leads to soil degradation, in which soil loses the ability to support other plants. And so, erosion is actually one of the major causes, which is where that topsoil, those A and O horizons, are actually disrupted. So, for example, by plowing. So, plowing, we're trying to mix the soil around, right? But a bunch of the soil is going to be lost in the process. And so we then just ruin the soil. That's terrible. So, a lot of this soil is just like the wind. It comes upon us and it goes, and then the soil is like, ah, just like those people where they saw all those landslides. So, the water and wind is really taking it away, and then the soil is degraded. So, topsoil can be lost in a single growing season, and yet it takes centuries to replace. Think about centuries. It's hundreds of years. All that topsoil had built up, and now it's gone. Just gone. Imagine how badly this is happening. So, a lot of machines can also compact the soil. It can deplete nutrients from intensive use of the land, irrigation, and chemical damage, including pesticides. These also contribute to soil degradation. So, all the things you'd expect. If you have machines going over that soil, that's probably not very good. And then we have nutrient depletion. We're trying to get rid of all of that terrible not terrible. We're getting rid of the good stuff. We're getting rid of the soils. And so that is not good because we're intensively using the land. And irrigation and chemical damage. Basically, anything a human wants to do to the soil, it's bad for the soil. And so we see that actually 17% reduction in food production has been prevalent in Africa and Europe because of soil degradation. Now, global climate change has actually impacted the soil degradation in varied ways. So, slightly warmer temperatures actually can increase decomposition activity and increase nutrient availability. So, this actually could help the soils. But the soils in other locations could also become too dry, which would mean that all the decomposition is going to slow. And so, climate change, mixed effects. And so, we can't exactly describe all of it, but there's also been speculation that there's more carbon storage, or not more, but there's an effect on carbon storage in the soils by climate change. But we haven't really seen too many patterns yet. That's why we need to go into more studies of these sorts of things. Okay, so then finally in our topic of soils here, we can talk about physical and chemical additions, which can be made to improve the quality of a soil. And so we can try to improve the soil, but usually it takes a lot of years for natural process to restore it. Now, soils with moderate temperatures and precipitation are usually restored as you would expect more rapidly than in those with extreme amounts of moisture or extreme temperatures. So, if we have like moderate amounts, we're good. It's like the Goldilocks zone. We're trying to eat that porridge that's just right, just same as the soils. And so that ends our discussion of soils here. And I am going to go ahead and give you the secret word for this science video. And that word is none other than Anthropocene. I hope you enjoyed this video and thank you so much. Next up, we're going to be going over water resources, so please stay tuned for that. Thank you.